Okay. Yeah. Oops. Okay. So today we will work with one shot information theory course. We'll study the notions of distances between probability distributions, and we'll also study something new called smooth one-shot divergences. So in the last lecture, we had done Shannon's noisy channel coding theorem and defined Shannon's relative entropy and studied its various properties. So we singled out data processing inequalities as the main property to analyze. And this is because relative entropy is the mother entropic quantity from which the other entropic quantities can be defined and their various properties reduced. Okay, so let us now quantify what we mean for two probability distributions to be close to each other. So the first measure of distinguishability is what is called the L1 distance. It's also known as the total variation distance. It's something which you've probably already seen. So a probability distribution is like a vector. Okay, remember our alphabets are finite size. So probability distribution is a finite size tuple, or it's a finite size vector. And we have the L1 norm on vectors, which is defined like this. So the L1 distance is summation over the sample points x of the difference of the values taken by P and Q, and then you have to put the absolute value side. So the L1 distance is a metric on probability distribution. So metric means it has to satisfy three properties. So first of all, it has to be non-negative, which you can see from the expression. Then it has to be 0 if and only if P is equal to Q, which you can also see from here. Like if even a single one of these quantities is non-zero, then the L1 distance is non-zero. It has to be symmetric, again from the definition you can see. And then it has to satisfy the triangle inequality, which follows because this absolute value symbol satisfies the triangle inequality. And because we are working with probability distributions, the maximum L1 norm of a probability vector, actually the L1 norm of any probability vector is 1. So the metric, the L1 metric on probability distributions ranges from 0 to 2. And you can again check the L1 distance is 2 if and only if the two probability distributions have disjoint support. Okay. Recall the support is the set of sample points x, okay, where the probability distribution is strictly greater than 0. Okay. So if P and Q have disjoint support, then the L1 distance is 2, easy to check. And even if the supports intersect in one point, you can easily check that the L1 distance is strictly less than 2. So far so good. Okay, any questions about the L1? No. Okay, so the reason we like the L1 distance is because of the next property. So if a subset of the sample space S has probability alpha under Px, then it has probability alpha plus or minus the 1 norm divided by 2 under Qx. Okay, so I should make the correction here. Okay, so I should put the 1 norm symbol out. So again, this is not hard to see. So let me, you could probably see this before, but let me draw a diagram in any way. Okay, so suppose we have two probability distributions P and Q, and this is the graph of the probability vector. So the x-axis denotes the sample space capital X, so let me even write that, and the y-axis denotes the individual probabilities Px or Qx. Okay. So really the L1 distance is the sum of the areas between these two curves. Okay, so let's see if I can draw that. So first of all, this is X. Okay. And the area of the two curves okay, it's a little difficult to draw, but okay, so maybe I'll draw it offline. So you can make out is the area between P and Q here plus the area between P and Q here. That is what enters this formula. Okay, and since the L1 norm of P as well as the L1 norm of Q is 1, okay, so there have to be points where Px is strictly bigger than Qx. There have to be points where Px is, so those are here, Px is strictly bigger than Qx. There can be some points where Px equal to Qx, maybe even more than 1. And there have to be points where Px is less than Qx. Okay? So the area between the two curves is basically those points where Px is different from Qx, maybe larger, maybe smaller. And those areas put together give me the L1 distance. Now, again, you can check that because the L1 norms of P and Q are 1 each, the area where P is larger than Q is exactly equal to the area where P is less than Q. Okay. So that explains the factor of 2 out here. And now, if I take any subset, this bound will actually be achieved if the subset is totally in the right side. Right side is this subset S consists totally of points where P is larger than Q, or it can be achieved if the subset totally lies on the left side. So these are the points where P is less than Q. In general, your subset will have some points from both the left side and the right side. So in which case, you can now easily realize that the probability of S under Q, okay, will be less than these two bounds, will be somewhere in between. Okay? But in any case, this is the worst case deviation you can have from alpha. So now if the L1 distance between P and Q is, let's say, at most epsilon, then the probability of any subset, so the probability of any event under Q differs from the probability under P by at most an additive term of epsilon over P. Okay. Is this clear to everybody? Okay.
What was the last comment about epsilon? What is epsilon? If P and
P minus Q L1.
Okay.
Okay, that's okay. So now we look at another measure of distinguishability. So this goes by different names. So in this course, we'll usually call it the fidelity. Again, there are slightly different definitions of this fidelity, but we'll take the most convenient definition for our purposes. So here is the definition that we will use. So the fidelity between probability distributions P and Q is defined by this expression. So the fidelity is also known as the Bhattacharya measure, and this is statistician Bhattacharya from Indian Statistical Institute, Kolkata. Okay, so in a paper in 1948, he defined this measure for, his statistical purposes, but it's a beautiful measure, as we'll see later on in the course. So what is the right-hand side? The right-hand side is a nice geometric interpretation. So take the vector square root of P. So this is same as the tuple P, but I take square root at each coordinate. So now the vector square root P becomes a unit vector in the L2 norm. Okay, not in the L1 norm, but in the L2 norm. So the L1 norm of square root of P will be larger than the L1 norm of P. Okay, and it can be quite large. You can go home and figure out how large it can be. Okay, but the L2 norm of square root of P will be 1. So similarly, this unit vector is square root of Q. It is length 1 in the L2 norm. And now this quantity, the fidelity, is nothing but the dot product between square root P and square root Q. Okay, and we know that the dot product ranges from 0 to 1. Okay, for unit L2 length vectors, it is 1 if and only if P is equal to Q, or else it's strictly less than 1. Okay, and you can again check that if the support of P is disjoint from the support of Q, then the dot product will be 0. If the supports are not disjoint, you can check that dot product is strictly larger than 0. So in that sense, it looks like some kind of mirror image of the L1 distance. Okay, so so for example, the fidelity is 1 if and only if P is equal to Q. Again, easy to check from this picture. So it's not a metric. Now it's not a metric. One thing is metric requires that if the two quantities are the same, then it should be 0. But here, if the two quantities are the same, then it is 1. You'll say, okay, big deal. Let me take 1 minus fidelity. But even that doesn't turn out to be metric. But some slight variants of 1 minus fidelity do turn out to be metric, and we can define at least 3 metrics using fidelity. So as the diagram shows, the first one is what is called the Hellinger distance between P and Q. Okay, so which is given by this formula, square root of 1 minus fidelity. Now, what is that geometrically? And the geometric picture makes it clear that this is a metric. Okay. So the Hellinger distance is nothing but the distance between these two endpoints. So put the origin here, draw your unit L2 length vector square root P square root Q. Then look at the L2 distance between the tip ends. This L2 distance is basically the Hellinger distance up to the scaling factor. Okay. You can easily check. Now, remember, fidelity is the cosine of this angle, okay, from the definition. Then the next distance is the purified distance, which has this expression. So in trigonometric terms, it is a sine of this angle. So it takes a little bit of work, but you can do some trigonometry and check that this is also a metric. It satisfies the triangle inequality. Okay. So sine theta is also a metric, purified distance. And the third metric is the arc distance. Okay, so arc distance is this APQ, which is nothing but theta itself. So in our language, it's cos inverse of the fidelity. But in terms of diagram, this is just theta. Okay, remember theta is in radians. So the angle theta is the same as the arc length theta out here. Okay, the circle is unit radius. So, so theta can be a metric. The angle theta itself can be a metric. Sine theta can be a metric, or the L2 distance between the tip ends, okay, can be metric. And you can go home and check out what this L2 distance looks like in terms of the angle theta. It has a nice trigonometric expression. Okay, any questions about this? So maybe just write it.
I can see the last two, but the Hellinger distance being a metric, I don't really. I mean, why is it?
That should be the easiest. The last two are more difficult because this is just the L2 distance between the tip ends. No, so take
So
PQR.
why that's a bit that I don't get.
I mean, the L2 is a metric, right? I mean, you believe that.
Yeah, L2 is a metric, but why is it the L2? Why is this equal to the L2 of the difference of the two vectors?
Oh, so that's the question. Yeah.
Yes.
Why is square root of 1 minus f the L2 metric? That's the
Yes,
question?
Yes.
Okay,
So that's the question.
So let me tell you what is this. So this is sine theta by 2. Maybe there is yeah, factor of 2. Okay, so this is your Hellinger distance. You can check that.
So I guess when we expand out root p minus root q the whole square, then I think we get right. I mean,
No, you don't have to do that. Yeah, I mean,
okay.
we will do that for a different purpose later on in the very next slide. But just use trigonometry. So this is theta, right? So the this length of the segment between the endpoints is 2 sine theta by 2. That's basically Hellinger distance. Okay. So the scale factors
Okay. I see.
don't matter so much.
Yeah, I see it. Yeah.
Okay. This is, I mean, 12th standard trigonometry, so we should go home and check. Okay. Any more questions about this? Okay. Another thing, the nomenclature purified distance actually comes from quantum information, so it will be in the second half of the course. Okay. Hellinger is after the name of a mathematician, and arc distance is the name that I cooked up. Okay. So we are trying to distinguish probability distributions, and we have come up with two measures of distinguishability: the L1 metric and the fidelity measure of distinguishability. So now we'll see what is the connection between L1 and fidelity. So P and Q are probability distributions on the sample space X. Okay, and here is the theorem that so in the middle I have the L1 distance, okay, divided by 2. It is lower bounded by 1 minus the fidelity. And from the expression, this is square of the Hellinger distance, right? and it's upper bounded by square root of 1 minus fidelity square. And if you remember the expression, this is the purified distance. Right? Hellinger distance, purified distance. Okay, so this is the so the connection is not tight. There are cases when the L1 distance is closer to the lower bound. There are cases when the L1 distance is closer to the upper bound. Okay, but so in fact it does range over the full gamut. But anyway, we have upper and lower bounds. So there is some control that if the L1 distance decreases, then we know the fidelity has to approach 1, and we have upper and lower bounds on the rate of approach. Right. So let's prove this. So this is where we use Ishan's idea of Hellinger distance squaring and all that. Okay. Okay. So start with the L1 distance. So we have this expression for the L1 distance, right? And we can lower bound it like this because square root p plus square root q is always larger than square root p minus square root q. And now if you expand this, remember the summation px, summation qx will go up to 1. Okay, their probabilities. So we end up with this expression. So that basically proves the left-hand side. For the right-hand side, again, expression for L1 like this. Then we apply Cauchy-Schwarz. Okay. So look at the dot out here. So we treat it as the dot product of two vectors. In the first vector, the x coordinate is given by square root p minus square root q, with the absolute value. In the second vector, the x coordinate is given by square root p plus square root q. So when you do Cauchy-Schwarz, we get this. And then you open this up and expand. So we have already done it out here. This becomes something like this. This also you can open up and expand, very similar to what we just did. And we get this expression, okay, which boils down. So this is the upper bound. Any questions?
Yeah, I have one question. Like summation of px plus qx, that part, how is that equals to 2? Like,
These are probabilities, right? They're probability distribution. Summation px will be 1. Similarly, summation qx will be 1.
Okay. So indeed. Okay.
Yeah. So I wrote out here px and qx are probability distributions.
Okay.
Okay. Any further questions? See, if px and qx are not probability distributions, then this picture doesn't quite work, right? I mean, if it's not a probability distribution, then this vector will not be of unit L2 length. Square root p will not be of unit L2. So we are doing all this under the condition that px and qx are probability distributions. And you derived. So again, this holds when px and qx are probability distributions. More questions? Okay. So now let's go over to the connection between relative entropy and these measures of distinguishability. So namely L1 and fidelity. Okay. So remember in the last lecture and even today, I repeated saying that the relative entropy is an asymmetric measure of distinguishability between probability distribution. So as you saw in the last lecture, the relative entropy is greater than or equal to 0 for any PQ, and it is 0 if and only if P is equal to Q. So, and it's asymmetric because relative entropy of PQ is not the same as QP. Okay? And this is a deep observation which will become clearer as the course proceeds. I mean, why the asymmetry is important and how we can exploit this asymmetry for our applications. Okay, so it's really a very useful quantity to work with. Okay, now can we relate these two measures of distinguishability, relative entropy and let's say fidelity? So indeed there's a connection. So fidelity squared is larger than this expression, 2 to the minus relative entropy. And so this actually implies something for the trace distance. So remember there was a bound between connecting L1 distance and fidelity, right? So I'm talking of this bound out between L1 distance and fidelity. if I use this bound, then I can replace fidelity by L1, and I can get this expression. Okay, so you can go home and work this out. Well, I think I worked it out here. Okay, so you can see it out. Okay, so what does this say? This says that if the relative entropy between P and Q is small, then their L1 distance has to be small. The converse is not always true. As you can cook up examples yourself, or we will see examples anyway as the course proceeds. So it's possible that two probability distributions are close in L1. I mean, let's say it's order epsilon in L1, but the relative entropy is quite large. It's not just a function of epsilon, dimension dependent terms start coming in, so on and so forth. So in a sense, this is the best that we can prove. Okay, let's prove it. So start off with the relative entropy, and here is really the brilliant idea: divide it by 2. So we have this expression out here, and because of the negative sign, I've taken the reciprocal in the logarithm, so it's log of qx by px. So then, I'll move this half in to the logarithm, and this becomes square root, and then I'll apply concavity of the logarithm. Remember, the log is a concave function, so concave means expectation of function values, okay, is less than the function value of the expectation. So let me draw a figure to remind you. So the log kind of looks like this, let's say. Okay. And concavity, if you recall, meant that this line segment joining 2 points in the curve, which is also called a chord, always lies below the actual curve. Okay. So average of function values. So let's say I take the function value, that means the point here, the function value, that means the point here. Their average will be some point on this chord that lies below the function value. So that means that is below the function applied to the average. So that's what I've done out here. So here the function is logarithm. And now if I do it, so lo and behold, I'll get this expression, which is the fidelity. Okay. So this proves the first inequality out here. And now to get the L1, I connect it to the fidelity by this. Okay. And then I apply the lower bound on fidelity, which I just proved, but I like this. And I finally get this inequality where we have used this property that e to the power x is larger than or equal to 1 plus x for all real x. So this part you can prove by simple calculus. If you're not aware of it already, you can prove that by simple calculus. It holds for all x. This is a very useful inequality, appears time and again in our proofs. Okay. So any questions about this proof? No? Okay, good.
If I'm not wrong, this is Pinsker, right?
Yeah, this is also known as, at least the second one is usually known as Pinsker's inequality. Yeah. So here is probably the simplest proof of Pinsker. So this is the simplest and also the best constant for Pinsker inequality that we get is by this analysis. There are other ways to prove Pinsker also, but I like this one. Yeah,
Pinsker is good only as long as the there's a trivial upper bound of 1 on the total variation distance or 2, whichever way you define it.
Yeah.
Beyond that, this inequality doesn't kind of give. Yeah, I mean.
Yeah. This doesn't count. This is more like if the relative entropy is a very small epsilon or something like that, right. Then this is square root epsilon. Yeah. So and for good reason, like which I just said a few moments before, that it's possible that P and Q are close in L1. Okay, let's say they are epsilon close in L1. I mean, yeah. So epsilon cannot be 0. If P is equal to Q, then L1 distance is 0 as well as relative entropy is 0. But it's possible that P and Q are epsilon close in L1, but the relative entropy is quite large. The relative entropy is no longer a function of epsilon, some dimension. Dimension means the cardinality of x. These kind of expressions will start coming in. Okay, so you can easily cook up examples like that, or as the course proceeds, I'm sure we'll see examples which happens. But you may be wondering, what can I say if let us say the relative entropy is something? I mean, moderately large. I mean, moderately large means it's much larger than 2, but maybe not as large as log x or something like that. Okay. Then can I say something non-trivial about the L1 distance? So one thing is, of course, if the L1 distance is 2, if that means the support of P and the support of Q are disjoint. So then the right-hand side, the relative entropy will automatically be infinite because support of P is not contained in support of Q. So this you have seen before. So relative entropy can be infinite, and this happens if and only if support of P is not contained in the support of Q. Okay. So we can already conclude that, let us say the relative entropy is finite. Okay. Suppose the relative entropy is finite, that means the support of P cannot be totally disjoint from the support of Q, which means on the left-hand side, the L1 distance is strictly less than 2. Right? So do you follow this argument?
Yeah.
Yeah. So, but you can do even better. So we will see as the course proceeds. So there are some beautiful things you can say about it. Okay, so we can say more quantitative things. If the relative entropy, let us say some K, okay, then I know it's strictly less than 2, but I can say that it is less than 2 minus something like 2 to the minus K. Like,
yeah, I think the intermediate inequality, the series of inequalities you have kind of stated, like yeah, so that doesn't become trivial. So for example, this total variation is less than or equal to twice the square root of 1
no,
minus
so yeah,
e to the power minus.
Yeah. So this never becomes trivial. Okay. I mean, throughout the range of from 0 to 2, this gives non-trivial results.
Yeah.
Okay. And good point. So the reason is there's a polynomial dependence between L1 and fidelity. Polynomial, whatever, square root also is like a polynomial. If I square it, I mean, it becomes some polynomial. Okay. So there's a polynomial upper and lower bounds between L1 and fidelity. Okay. Whereas between L1 and relative entropy, there are exponential connections. Okay. So, I mean, it's not clear from here, but I mean, it's clearer from here. Okay. So, so L1 and fidelity exponentially are polynomial related, but you can see that fidelity is exponentially related to the relative entropy. Okay. So, so this means that even the L1, strictly speaking, is exponentially related to the relative entropy.
So I have a question. So it seems like the last step of the proof where you go from fidelity to L1. There we use this very gross approximation, right? E power x greater than 1.
Correct.
So that is where the weakening happens, right? This very last inequality is where the weakening happens, because if
yeah, I mean, between L1 and fidelity, well, actually the weakening has already happened before, because the fidelity can be at most, yeah. So let us say, so the same thing is possible, which is not immediately clear. I said the L1 can be about order epsilon, whereas the relative entropy can be quite large. Okay, so this means that the fidelity can be close to 1 minus epsilon, but the relative entropy can be quite small. Okay, this inequality can look like something like 1 minus epsilon on the left, and 2 to the minus square root log x on the right, something like that. That is okay, which is still a pretty horrendous quantity, 2 to the minus x square root log x. So it's not immediately clear from here that these things can happen. I mean, one may be tempted to think, as Shantanu just said, that all the weakening occurs here. Like here, you can see the exponential connection between relative entropy and L1. Okay, and that exponential has disappeared here because we use this very gross exponent thing. So you may be tempted to think that this exponential relation is only introduced here, but that's not true. The exponential relation already has crept in here. Okay, so this, I mean, you can only see by example or with a deeper understanding of information theory. But but the problem has already crept in. Yeah. So in that sense, like going from here to here actually hasn't aggravated anything. All the aggravation has occurred here. Okay.
Okay.
Yeah. So as I said, I mean, if two things are polynomial related, you can think of them as equivalent. Let us, I mean, believe that. I mean, we all believe all problems in P are equivalent in some sense. It's just like that. Okay. So L1 and fidelity are equivalent. So, so really, I mean, the exponential gap, as suggested by fidelity here, is genuine. Yeah. Any more questions? Okay, if not, let's go ahead. So good points, actually, which I think we should. I will try to address them in examples in later lectures. Okay. So now we move on to relative entropy. We will look at generalizations of relative entropy. So they are called divergences, and there's a whole family of them indexed by parameter alpha, and they were proposed at least implicitly from the work of the probability theorist Renyi, Paul Renyi. Yeah. Yeah. So let's say, so Px and Qx are probability distributions on the alphabet X. Take the parameter alpha, given like this. So basically, alpha can be any number from 0.
Sorry, I'm just going to interrupt for one thing.
Why?
So going ahead, when we want to define a divergence, the only thing that we want the divergence to satisfy is the data processing inequality, right?
Yes. I mean, if we define, okay, so what is a divergence? So divergence, loosely speaking, is any asymmetric notion of distinguishability. Okay, so if P is equal to Q, the divergence better be 0. Okay, and if P is not equal to Q, the divergence should be greater than or equal to 0, let us say. Okay, and the desirable, it is desirable that it should also satisfy data processing. So always divergences, I mean, we may define something and loosely call it a divergence. It may not satisfy data processing inequality. If that doesn't happen, we'll point it out and we'll take steps to remedy it.
So why I ask this question is, so one, that why would I come up with this formula? Why? And the second question is, there is this whole axiomatic derivation of mutual information and these sorts of things, right? So
yes, there are axiomatic derivations of these Renyi divergences also. So the Renyi divergence possesses some nice properties, and I mean any measure that has these nice properties has to be a Renyi divergence. I mean, you can prove those things. So that viewpoint is there, but so those are all good viewpoints. But for our purpose in this course, we'll just see that some of these Renyi divergences are very important for our one-shot applications. Okay.
Okay.
So, I mean, we will not go deeply into Renyi divergences for their own sake. There are people who do that. There are all kinds of relationships between Renyi divergences and the alpha parameter and all that. So we'll not do a detailed study of alpha, but I'm just saying that so that you have some familiarity with the broad literature, and we look at some special alphas which are really useful for our purpose. So, but it's good to know that there is a unifying picture where alpha can be any parameter in this range.
So basically, we are taking an operational view, is what you mean?
Yes. We are taking this course is an operational view. In this course, we want to solve information theory problems in the one-shot setting, and if possible, we want to beat asymptotic IIT. Okay, and we are taking an operational view. We'll take a very reductionist view. We will define as little quantities as possible. Okay, prove as little basic theorems as possible, and try to extract the maximum juice from that. Okay.
Okay.
And hopefully by the end of the course, we'll be amazed what we can do with such little preparation. Okay. Yeah. So this alpha parameter is something in this range. So note that alpha is not equal to 1. I'm not allowing alpha equal to 1 out here. Also, I'm not allowing alpha equal to infinity. But I'm indeed allowing alpha equal to 0. Okay. So this is the alpha parameter. So the alpha Renyi divergence is defined like this. So you can clearly see why I'm not applying allowing alpha equal to 1, because I'm dividing by alpha minus 1. You can also sort of guess why I'm not doing alpha equal to infinity, because what do I mean by dividing by infinity? Okay. But for the rest, this formula makes sense. And here I am. Okay. And note that just like the Shannon relative entropy, so this divergence, at least the notation suggests that it's something like the relative entropy. It can very well become infinite, okay, sometimes, and we will see, I mean, if it becomes infinite. Okay, so this is the definition. So for alpha equal to 1 and alpha equal to infinite, we'll also define d alpha by taking the limit. Okay, so we'll take this formula and take the limit. Okay, so we'll do that in the next slide. But let's stick with the definition for alpha now. So the alpha Renyi conditional mutual information and the conditional entropy are defined in the usual manner. So for Shannon relative entropy, I had only defined the mutual information and the condition entropy. But people who have done some basic information theory course, you would have seen even the formula for conditional mutual information, which is very useful for some applications. Okay, so it turns out even the conditional mutual information can be defined in terms of these divergences. So really, I mean, the divergences are the mother entropy quantities. Okay? So if you're in the world of Shannon and asymptotic IID, relative entropy is still the mother quantity for conditional mutual information. So the conditional mutual information is defined like this. Okay, it's this divergence. So this is the mutual information between X and Y condition on Z. So it is the divergence between the joint probability distribution on X, Y, Z and the second probability distribution, which I define like this. So pick a sample from the margin on Z and condition on Z, pick a sample from X, and independently condition on Z, pick a sample from Y.
So, I mean, there should be D sub alpha here.
There should be D sub alpha, yes. So, right. So the second probability distribution is basically telling us that look at the distribution where the marginal on Z is the same, and the marginal of X condition on Z is the same as before, marginal of Y condition on Z is the same as before, okay? And X and Y are independent given Z. So that is this unique probability distribution that we are talking about. Okay, so as Ishan likes Markov chains, so the second probability distribution actually, I just said, X and Y are independent condition on Z. So you can say that this is a Markov chain. Okay. So I have achieved this Markov chain that X and Y are independent condition on Z. Okay, while keeping the marginal on Z the same, then the condition of X given Z the same and the condition of Y given Z the same. So is this definition clear? So you can now go home and check, at least for the Shannon relative entropy, that you actually get the Shannon conditional mutual information from here. And the condition entropy is defined the same as before. So log X minus D alpha Pxy, and now the second probability distribution is the uniform probability distribution X times the marginal on Y. Okay? So X and Y are independent out here.
I just have a question, quick question. So
yeah, and let me finish. So the unconditioned mutual information and the unconditioned entropy follow from the above definitions when the conditioning systems have cardinality. Okay. Yeah. Questions?
yeah, so is this is H alpha X given Y? Is this also equal to negative of D alpha Pxy identity on X tensor P on Y?
Yes, indeed. Which you can easily check.
Yeah, okay.
Yeah, but I did not use the definition because if you put in the all ones vector on X, so what Shanton just said, let me write down. So he's an advanced student. So yeah. So he just said that this is actually equal to So he has basically removed the log x out here. Okay, but the price that you pay is that, so the vector I put on x is no longer a probability vector, it is the all ones vector. Okay, so it's very much like the uniform distribution, except I've scaled up the uniform distribution by mod x. Okay, and I've got the all ones. So if you do that, you can still define d or d alpha by the same formula as before. Okay, and it turns out that these two expressions are the same. Okay. But I did not do it because I choose to use d and d alpha as measures of distinguishability between probability distributions. So everything entering d has to be probability distribution. So that's why I wrote this definition. And if x and if z here and y here have cardinality 1, then I get the unconditioned definitions accordingly. Further questions? No? Okay. So let's see what we have learned. So we have defined the Renyi entropy for alpha, but we have avoided alpha equal to 1. We have avoided alpha equal to infinity. Okay. So let us see what D0 looks like. Okay. So it turns out that D0 has a nice expression like this. So it is the negative log of the mass under the probability distribution Q of this set. So what is this set? This is support of P. So recall support of P are those sample points X such that Px is strictly positive. Okay. Now support of P may not be the entire space X. Okay. So if it is the entire space X, then of course Qx is a probability distribution. This will sum to 1 and the log will give me 0. Okay. So quite often D0 PQ is 0, even if P is not equal to Q. So as long as P is full support, D0 is a useless quantity, it is always 0. Okay, so I don't have any strict positivity for the Renyi divergences anymore. Okay, so of course, if P is equal to Q, so at least this is clear to everybody. If P is equal to Q, then this quantity will sum up to 1 and the log will give me 0. Okay, so if P is equal to Q, D alpha is 0. So that much I'm sure of. But there can be tons of examples where P is not equal to Q, but still D alpha is 0. So, so this is starkly clear for D0. As long as P is full support, the 0th Renyi entropy will always be 0. So the fun comes when P is not full support. So that's really what I'm talking of. So when P is not full support, I look at the mass of the support of P under the probability distribution Q. Take the logarithm of that, that's D0. Okay. So you may be wondering, I mean, why one has to bother with such a useless quantity. But if you bear with me for 1 or 2 more lectures, you'll see that D0 can be very, very useful. Okay. But let us go ahead for alpha equal to infinity and alpha equal to 1. So these were the alphas that were missed out by the definition. Okay. So as I said in the last slide, that to define Renyi entropies for alpha equal to 1 and alpha equal to infinite, we have to take limits. So you can do it and you get this expression. So d infinity of P with respect to Q is given by this expression. So what is this? Let's see. So this d infinity is the minimum threshold lambda with the following property, that for every sample point x, the ratio px by qx is less than 2 to the lambda. Okay. So of course, if a particular lambda satisfies this property, then any lambda prime bigger than lambda will also satisfy this property. So that's why I've taken the minimum out here. So lambda is the minimum threshold, or in other words, look at the ratios px by qx, okay, and look at the largest such ratio. Take the log of that. That is the minimum lambda. Okay, so that. Okay, so is this definition clear to everybody? Okay, and it turns out D1 is nothing but the Shannon relative entropy. So let me at least draw a diagram, or maybe just tell you. This is just what I say. So d infinity is nothing but this. So this is written in this fancy notation. But again, there is a reason why I chose this notation. It will become useful in our later formulas. Okay, but for now, I mean, this is what is d infinity. Remember that these are divergence. They can very well be infinite for P and Q, and you can easily see that if the support of P is not contained in the support of Q, the maximum here becomes infinite. So the infinite is infinite if support of P is not in support of Q. In fact, this is infinite if and only support of P is not contained in support of Q. And then there is D1 also. And D1 also has the same infinity property.
Pranab,
So,
can I just
yeah.
stop you for a minute? So,
Yeah, you can stop me for more. So I will actually pause recording for 5 minutes, and then you can try to prove it by basic calculus.
Yeah, that's exactly what I'm going to do. So, stop recording.
But any other questions? No. Okay. So let's say it is 12:37 now. So let us say we meet at 12:45.
So I mean, I don't have a proof, but here are a couple of things that we can try. So one thing is this, but all of the so I mean, take the Cauchy shots of whatever is inside. Okay, so that will sort of give you this break the summation. Okay, but I don't
try to prove d infinity or d1.
Both. I mean, something should give sort of something, but
You are breaking the summation here.
yeah, I'm breaking the summation here exactly. I don't know whether that will work. Another approach is that which might be more natural, is that you take P also. I need to get the summation outside somehow. So P alpha x over Q alpha x times QX. This I lower bound because of this concavity with by taking the summation and QX outside. Okay, and then I can take the alpha out, and the limit to infinity will just cancel the alpha over alpha minus 1. But that is giving me that this guy is greater than equal to summation qx log px over qx, which is not what we want.
Can we use AMGM inequality?
Sure.
AMGM inequality on log.
Yeah, so AMGM is sort of AMGM here.
Sure.
Like
I mean, yeah, you can use whatever. But yeah, I mean, we are trying to prove it, right? So it's fine if you use inequalities, but then when you take limits, somehow they should become equalities. You can ensure that.
No, but Pranav, one thing is that, I mean, shouldn't this be p to the 1 minus alpha q to the alpha? Because the lower bound I just proved is it's giving me dqp, not dpq.
Okay, so anybody else has any other idea? So there is AMGM, there is some Cauchy-Schwarz and convexity, but all these are giving inequalities, and then you are left with the trouble of showing that the inequalities become equalities when you take limits. So maybe you have to sandwich between two inequalities if you have to do such things. Any other ideas? No? Okay, so let us see. So actually, I mean, you, as I said, just use simple calculus. You don't have to work so hard for this. Okay. So let's try to prove the first one. So as I said, d infinity, right? In the previous thing, I told you what is d infinity. It is the maximum value of px by qx, right? So we are using that. So take the maximum value of px by qx, call it 2 to the power lambda. Okay, and let us say this maximum is attained for a particular x that we call x infinity. It might be attained for several x's. Take any one of them and call it x infinity. Then what do I have? Then I have this inequality, right? So here is the expression in my Renyi entropy. To lower bound it, I'll just instantiate it for x equal to x infinity, and then I get the left hand side. Okay, and to upper bound it, I know that for every x, px is less than 2 to the lambda qx, right? I mean, because this is the max, I know that for every x, px is less than 2 to the lambda qx. So that's what I will do. I will use that upper bound and it will become 2 to the alpha lambda here. And I'll get p to the alpha x is less than 2 to the alpha lambda q to the alpha x. And then the whole thing will become summation qx, which is 1. Okay, so overall, this will simplify to 2 to the alpha lambda. So this Renyi quantity is upper bounded by 2 to the alpha lambda and lower bounded also by 2 to the alpha lambda. And then there is this fudge factor out here. But remember, this is a constant which is independent of alpha. Okay. So it's just a property of the probability distribution Q. So now if I take the limit as alpha goes to infinity, okay. So we get so what I'll have to do, I'll have to take the log of this. So the log gets sandwiched between these two quantities. Then divide. So taking the log of this will give me alpha lambda on the right hand side and alpha lambda minus some log qx infinity. So hello.
Yeah. Yeah.
Can you hear
Yes,
me?
we can hear.
Hello.
Yeah.
Can you?
I mean, I can hear.
You can hear me. Oh, no. So something happened. I think the Bluetooth ran out of charge. Okay. But you can still hear me, right? So this is from the computer speakers now.
Yeah.
Okay, good. Yeah. So now if you take log out here, right? Expression. Now if I take log of this quantity and divide by alpha minus 1, so I have an upper bound of alpha lambda by alpha minus 1, lower bound also of the same thing, but there is a minus.
How are you getting this upper bound? How is the summation being upper bounded by 2 to the alpha lambda?
So I have this. No, I have p to the x is less than 2 to the lambda times q to the x. Qx. So let me write it down. What I'm using. Oh, this is kind of class tool. Class tool.
So it's just like average is less than equal to expectation is equal to maximum. That is the second part of the inequality.
Yeah. So px is less than 2 to the lambda q. So this holds for all x, by the way.
Okay. I see. Okay.
So that's what I've used out here. So that's it. Taking the limit as alpha goes to infinity, we get the above expression for d alpha. So the above expression means this just tells us that d infinity is the maximum value out here, which I just told in the previous slide, and that is written in this fancy language. And as I said, d infinity is finite if and only if support of p is contained in the support of q. So is this part clear? The first part, everybody?
Yeah.
Okay. So let's go to the second part for alpha equal to 1. So we apply L'Hopital's rule. Okay. So d1, we have to take the limit as alpha goes to 1. Okay. Now, so what is the problem? Let us try doing it. So as if I put alpha equal to 1, so what do I get? The numerator is log of summation x px. So this q to the power 0x is always 1. So now summation x px adds up to 1 because it's a probability distribution. The log is 0. So I get a 0 upon 0 scenario. So whenever you have 0 upon 0 scenario, to take limits, you can use L'Hopital's rule, which you recall very well from 12th standard. So just take the derivative of the numerator, derivative of the denominator, and again try to take the limit. So this is so the derivative of the denominator is very simple. It's 1. So that's why I've not even bothered to write it. So I just have to take the derivative of the numerator, and this whole expression, which you can easily check, is the derivative of the numerator. Now, because our logarithms are to the base of 2, I have to go to natural logarithm. That's why this ln2 sneaks in, and this expression comes out here. But anyway, now I can move this ln2 back here and go back to log to the base 2. So in the numerator, I get this expression. I take the limit as alpha goes to 1. So you can see that this becomes q to the power 0, which is 1. This is px. So this is px log px. And out here, this is px times 1 times log qx. And the denominator is just summation px, which is 1. And you can see that the numerator is now exactly the Shannon relative entropy. Okay. So is this proof clear? Yeah. So what have we proved so far? So recall this was the definition of the Renyi entropy. And for alpha equal to 1 and alpha equal to infinity, we had to take limits. Then at least for alpha not 1 and not infinity, it is clear that this expression is continuous in alpha. Okay. But because those limits exist and they exist nicely, what you've actually ended up proving, okay, we have not completely ended up proving, but a little bit more effort, you can prove that d alpha is continuous even at alpha equal to 1 and at alpha equal to infinity. Okay. I mean, continuous at infinity just means to say the limit exists and is finite, which you have indeed shown.
You could just define the function at those points to be those values.
Yeah, for one, I've shown that the limit exists. Then you have to show that it's continuous there. So a little bit more work, but it's essentially elementary calculus. So d alpha is continuous in the parameter alpha for alpha in this closed interval. Okay. So it's an important result. Nice mathematical result. Then again, okay. So so let us prove the next point that d alpha is positive. So let us say I take alpha greater than 1. If alpha is greater than 1, then yeah. So then yeah, actually let us keep the positive later because it will become clearer when we do the non-decreasing thing. But anyway, at least it's clear that if p is equal to q, d alpha is always 0. Okay. This is true for irrespective of alpha. But as we saw for the d0 example, d alpha can be 0 even if p is not equal to q. So it's not strict positivity. Here is an important property that d alpha is non-decreasing, or more simply is basically increasing in alpha and is increasing for this entire range. Closed interval 0 to infinity. So let us try to prove it. So the proof splits in two parts. We will first look at d alpha is increasing. So what we'll do is we'll take two Renyi parameters alpha and beta, where alpha is less than beta. So the first case is when alpha and beta lie to the right of 1. The second case is when alpha and beta lie to the left of 1. Okay. And then when the parameter is 0 or the parameter is 1 or the parameter is infinite, things will just follow by continuity. Okay. So let us see when I'm strictly to the right of 1. So the basic fact that I'll use from calculus is this function x going to x to the power theta is convex for theta greater than 1. So for the first case, when alpha and beta to the right of 1, I'll take theta to be this quantity. So you can easily see it is greater than 1. And then I'm going to use the convexity of this function. So what does this function look like? Let me draw a diagram. So this is the function x to the theta, right? And basically it looks like the parabola x square, I mean, kind of like that. Okay, so it just goes up like this. And here is convexity. So convexity was the opposite of the figure for concavity. So it basically says that the chord lies above the curve, or in other words, the average of function values is larger than the function value of the average, right? So average of the function values at the two endpoints is some point in the middle of the chord, this lies above the graph, which means it is greater than the function value of the average. So that's what I do out here. So this is the average of the function values. So I am evaluating the function x to the power theta at these values of x, p to the alpha minus 1, q to the alpha minus 1. Then I'm taking the average under the probability distribution p. So the left hand side is the average of the function values, and the right hand side is the function value of the average. So I put it in, and you can check this. And now it's just manipulation from here. I just take the
No, that step is fine, but how do you get the implication? That's what I'm not getting.
Huh?
How do you get the implication? So this step is fine. This step is fine.
This step is
Yeah,
fine.
yeah. So what is bothering me is what comes the next line. That this Jensen implies that summation p beta x q 1 minus beta to the whole power 1 minus 1 over beta minus 1 greater than summation.
You just raise everything to the power 1 by beta minus 1. Yeah, that's all. It's the same as the previous thing. So you simplify the previous thing. Remember, I mean, this is alpha minus 1 by alpha minus 1 that goes inside, and when something happens, you'll need pen and paper to work it out. Okay. I mean, I'm not going to do everything on the slide, but this is an easy check. The main thing is you raise everything to the power 1 by beta minus 1. And this is where we use the fact that beta is bigger than 1. In other words, beta minus 1 is bigger than 0. Okay. So I'm using that if x is less than x prime, then x to the power let's say delta is less than y to the power delta if delta is bigger than 0. And if delta is less than 0, the inequality reverses, which will become clear in the next part. Okay. So is this part clear, the first part? Yeah. Okay, so let's do the next part. So now I'm taking alpha and beta to the left of 1. So now here is the value of theta that I take. Okay. And note that theta is still bigger than 1. And then I apply the convexity, Jensen. So this, so start off with this expression for the convexity. Average of function values is greater than function value of average. And now I raise everything to the power 1 by alpha minus 1. Now remember, alpha is less than 1. So 1 by alpha minus 1 is a negative quantity. So now I'm using the fact that if x is less than x prime, x to the power delta is greater than x to the x prime to the power delta if delta is less than 0. So the inequality reverses out here. But in either case, I have proved what I wanted. So if you notice, this is d alpha, this is d beta. Okay. So of course, if you take logarithms for this there. And this is d alpha, this is d beta after taking logarithms. And now I just use continuity of d alpha at alpha equal to 1 and at alpha equal to infinity to complete the proof. So I've ended up showing that d alpha is increasing for alpha. And now, okay. And now I know that d0. Okay. If you remember the expression for d0, d0 is a positive quantity, right? It was negative log of something, and that something was less than or equal to 1. So d0 is a positive quantity, which means that d alpha is a positive quantity for any alpha and any p. Any questions about this? Okay, so we will stop here for today. And I will see you on Thursday. Please make use of the Slack channel, the discussion channel there. Any last questions? If not, I'm going to stop the recording here and see you on Thursday.